Okay, welcome back, everybody. Today is Monday, the last week of the summer. So today, let's just continue. By the way, do you have any question about updates about announcement about Friday, June 18? I think I went through it. So let's just take a look at the new announcement I posted today. End of semester session announcement. Here we go. So this is very, very important announcement. Okay, so let's just take a look at it. I sent it today, this morning, so most of you actually haven't looked at it yet. That's fine. Please spend some time read through it. Two items. Number one is, of course, end of the semester course evaluation. I'm interested in hearing two things. One is a very positive appraisal and stuff like that. Since I'm teaching this class very uniquely, I started to do lots of practice, a new attempt under the COVID. One of them is digital pen, and then lecture or video capture, and also OneDrive submission, completely paperless, stuff like that. Did you like it? Or if you feel, hey, you should have done this way or that way, I would like to hear. Okay. So please participate, end of the semester course evaluation. Now, important thing you want to hear is if you do participate, end of the semester course evaluation, I give you a little bit of gift, not much, little bit, and not so bad. So if you do this, okay, before noon of Friday this week, if you participate this end of the semester course evaluation, I give you two things. Number one, of course, quiz 3B. Right now, everybody, the score is dropped temporarily. I will offer you 10 out of 10 score for you because I feel a little bit guilty because, hey, wait a minute, this quiz problem might be a little too challenging. Oh my goodness, I'm not sure. Well, I'll give you 10. Okay? Number two. And suppose if you have a bad day, well, everybody have a bad day. Today, I just did a 2 out of 10 of quiz. Well, if you have that kind of stuff, I'll let you drop it. Okay? So two things. Okay. So how can you get that? Number one, first, complete the end of the semester course evaluation online. Then and only then, you please send me email. Just like this. Okay, Dr. H, I did it. Okay, please don't write to me because I can check it. Oh, Dr. H, I did it. I did the end of the semester course evaluation online learning. Please don't forget your name and ID. Okay, and please drop this quiz. Well, I don't know which quiz. I did quiz 2 out of 10, or I didn't even take the quiz 2, 0 out of 10. Please drop it. I'll drop it. Okay. One bad quiz score. Plus, I give you 10 out of 10 for quiz 3A. This is out of my own guilt. Okay. If you don't do this, of course, quiz 3B is still dropped, and I'm not going to drop you another bad score. Okay. It's not so bad. I mean, if you completely ignore it, it's not so bad anyways. But if you participate, I give you a small incentive. Okay. Next is end of the semester policy. It's just the standard stuff. I'm going to close out Canvas gradebook. Canvas gradebook. That's where I store all your course grading score information. I'm going to close it out on study day midnight. Okay. So if you discover any error or mistake of score, please let me know before midnight of Friday. Okay. So midnight of Friday, I'm going to basically finish up all the grading. I think only exception is final. So except the final exam, you have all the grading score is up on Friday, study day. And then midnight, I'm going to close it. Okay. So please, just to do a double check, I don't want to see any errors. Okay. Any question here? Just the standard things. So please read through this. Okay. End of the semester course evaluation is due this Friday noon, study day noon. Okay. Let's move on. So I think we stopped at the class example 3 came 4. Shear moment diagram. So I think before we draw shear and moment diagram, this is not even a beam. This is a assembled beam, making your life more miserable. In other words, you have two free body diagrams, and you have 1, 2, 3, 4, 5. How many unknowns do you have? Anyways, so you have more bodies. So each body you're going to apply up to 3 equations of equilibrium and then solve those unknowns simultaneously. So first of all, your first task is to find out those support reactions, right? This is a fixed support reaction. This is a pin support reaction. This is pin, and this is rotor support. So you have to find out not all of those things only you are interested. In other words, you're not interested in Bx and Na because those are normal forces. It's not going to come into shear moment diagram. So I don't even try to attempt to find those things. So I wanted to find out moment reaction Ma, shear support reaction Ba, pin of By, and rotor support reaction Cy. Okay, that's the only thing I found. And then I assembled again, trying to construct this as a composite beam. If you assemble, the support reaction at the pin B goes, disappears, right? Because I assembled up. But this is the external support reaction moment and shear. This is a external support reaction shear. This is externally applied bending moment. This is distributed loading. This is a point force. So out of this configuration, you want to draw shear and moment diagram. Okay. So let's just, do you have a handout, by the way? I would recommend you looking at a handout because that's probably the only thing you're going to see in exam and quiz. So if you have a handout with you, let's just take a look at it. Okay. I think I'm going to bring up handout too. Okay, so where is the handout? Okay. So this is an important handout because I'm going to give you this for your final exam and also next quiz. This is only information you can access. Okay. So please keep it handy. Okay. So now, starting with the shear diagram, of course you're going to start with 0. And then here at the very end, you have 1016.667 shear force going positive upwards direction. So you're going to have a jump this much. Okay. So what is this value here? Obviously, 1016.667 pounds right here. Okay? And then what happens? It stays constant for a while, right? Until you hit this force. 700 pounds force gives you what? Gives you some kind of change of the shear. What is it? Going down, isn't it? How much? 700 pounds. Making sense? So, what is the value here? 316, that's right, 0.667. So in other words, starting with 1016.667, then you hit 700. So this minus 700, 316.667. That's right here. And what happens? Stays constant, right? Then you begin having something. What's that? This is a distributed loading. So what does this distributed loading do for shear diagram? Anybody? Please tell me. Slope is a, yeah. So this is the magnitude 150. So now all of a sudden you introduce the slope of the shear diagram. Slope is a negative of magnitude. So all of a sudden you have a straight line with a negative slope with 150 pounds per foot. Okay? Now I'm going to actually do this. One thing I know is at the very end you have a support reaction 583. So I know I have to go back to 0 at the end anyways. So I kind of know right here you have a jump happens to 0. And I know this value. You know this value, do you? What's this value? What's this value? Minus, yes, minus 583.333 pounds. That's right. And I'm going to draw a straight line in between. Straight line with slope. Slope is negative 150 pounds per foot. So that actually gives you this crossing point. Do you know where? You can determine this crossing point if you need to, right? You can tell 316.667 minus 150 times x is equal to 0. What is x? You can find it, right? If you need to. What is x, by the way? I'm kind of curious. So I'm going to do a quick math to find out this crossing point. So this crossing point can be found starting from 316.667, subtract 150 pound per foot times x, set equal to 0. X equal to, measure from here.
You got it.
You got it. 2.11? Okay. 2.11 foot. That's right. So in overall big picture, that's location is what? So this is the location. This is 8 feet, 4 feet, and 2.11 feet. You have a 0 shear point. Okay, so suppose if I ask you, okay, so what is this location? You know how to find it. You have to draw a shear diagram, and you know this is 8 feet, this is 4 feet, this is 2.11 feet. X equal to what? 14.11. That's the location where shear becomes 0 internally for this beam. Important information. Okay. So next is moment diagram. Moment diagram requires shear diagram. Okay, so let's very carefully approach it. So first of all, of course, start from 0. Then you have a huge reaction moment shows up here. Reaction moment 9,400 pound-foot. Is this positive or negative? This is actually negative. So that means, let's just go back and take a look at the handout. So this is a positive, okay? So that's the sign convention. So let's be careful. So if you apply the moment reaction this way, it's going to be negative, okay? So let's be careful.
Wait, but on the graph it shows like a huge drop in the.
That's right, huge drop in the moment.
But that's for it being counterclockwise.
Ah, okay. Sorry, let's take a look at M1. M1, sorry. So this is the external moment. So this is the point moment applied. It's going to be, yeah, this is negative. That's right. This is negative. Yeah, that's right. I'm talking about negative. Okay. That's why it's negative. So this is going to be a huge drop right here. This much. So obviously you have minus 9,400 pound-foot moment to begin with at the very end.
But in here you have like the same direction of moment and it goes up.
Yeah, it should go up.
Let me double check. Yeah, sorry, sign convention wrong here. Because I'm saying this is unknown direction, and then I said this is positive, and then I got the positive value means this is the direction. Okay. Yeah, so
I think you should have done minus on the first one when you computed it. So it means like that direction. Then minus.
yeah, I guess so. So I think my problem is, okay, yeah, I guess you're right. Since this is a sign convention, I should have done, okay, let me just correct. Since this is a sign convention, this is positive direction, then I got minus sign comes up, right? So, yeah, so that means in reality, this is actually opposite. Sorry about that. Yeah, I think so. Good point. So this is in reality the direction, isn't it? Because I'm taking this positive. If I do that, MA comes up with negative. Negative. That's right. So that's why negative.
Wait, so since you changed the direction of what's positive in the moment?
No, this is just basically any arbitrary choice. Because I arbitrarily said this is positive or that is positive. That's arbitrary.
So I could have taken like you took in the beginning.
I guess the important thing is this is the sign convention. This is just arbitrarily said, hey, that's just some moment, and that's just temporarily said this is positive direction. This is not sign convention. This is sign convention. So if you stick with sign convention, it's actually negative. I think that's what the problem really is. Okay, so that means let me just fix here, since I just took everything wrong direction. So this is this is positive. Sorry about that. So this is positive, and this is positive, and this is positive. Then it's going to get negative. Okay. Then following through sign convention, it's going to be this direction. That is negative. Okay. That's what it is, I think. Is that right? I hope so. Okay. So now, so this is negative. That's right. Negative jump at the support reaction here to begin with, okay? And then you know that magnitude of the shear is 1,016.667 from here all the way to 700 pounds external force here. So you have, okay, you have a linear function with the positive slope 1,016.667 from here to there. Okay, so from here to there, you have linear function in which you have a slope 1,016.667 pounds. Okay. it actually gives you the value right here. What is the value right here? You know this is 8 feet. So minus 9,400 plus 1,016.667 times 8. That is the value here. Still negative though. Anybody?
Minus 1,266.
66. Correct.
0.66.
0.667. That's right. Let's just make it 1267 to make it simpler. Pounds. So you get this value by computing. Starting point is minus 9,400. You know the slope. Slope is 1,016.667. So minus 9,400 plus 1,016.667 times 8 feet gives you minus, still minus 1,267 pounds. Foot-pound, sorry, foot-pound. Pound-foot. Okay. Then after that, what happens? Well, the shear changes. That means the slope decreases. So you are going to still climbing up, but decreased slope. Okay, you can still determine this value. You know this value right here?
I think it's supposed to be 0.
So no, it's not going to be 0 because you can determine this value minus 1,267 plus 316.667 times 4.
I got 1,000.
It's just still negative, isn't it? Or is it plus?
Exactly 0.
It's 0?
I got
About 0. Okay. Okay. Good. About exactly 0? Cool. Okay, so let's just draw about the 0 right here. It's a nice information. Right here, internal moment gets 0. Okay. Now what? Oh my goodness. So this is something interesting. In other words, slope keeps changing. So you are going to expect this kind of thing, isn't it? This kind of thing. In other words, slope becomes this. Important thing is, obviously right here, you hit the peak value. And then right here, obviously, same value as the moment. In other words, this is negative 800 pound-foot. Okay? And then at the very end of it, you are going to have jump of moment because of this externally applied moment. Important thing about this is sometimes people want to know this peak value. Peak value here, how can you determine this peak value here? That's this area, isn't it? You understand that? So 316.667 times 2.11 divided by 2. What's the value? 333 point something, 334 pounds, foot-pound. Right here. Good. So that's shear and moment diagram. So you really need to understand what it means to have a shear diagram, moment diagram. Now, if I give you a quiz, okay, this Thursday, shear moment diagram, give you 25 minutes. I think I would say it's impossible to draw a shear moment diagram unless you really understand, have a mastery skill of what it means to draw it. In other words, if you have a point force, you have a jump. If you have a distributed loading, this is going to determine the slope. The magnitude of shear determines the slope of moment. Okay? Change of moment is the area under the curve of shear. Change of shear is area under the curve of this distributed rolling. Stuff like that. Everything is listed in your handout. Okay, so how much do you have, how much understanding do you have for this handout is the key. That is something called skill set. People expect from you. Okay, so in other words, people actually trust you so that you can design that huge building's beam. What's the material? What's the cross section? What is the internal shear moment development? Where is the peak point, critical point? If it fractures, what kind of fracture you're going to expect? Those are the kind of things people expect you. Okay, so this is the beginning, first step, this Thursday. So be ready for very challenging. Well, it's not very challenging. It's a quiz. It's a quiz. Okay. If you seriously do your homework and it's a quiz, you can solve it. So please show me your guts as an engineer, please. So this is, once again, this is quite important information handout of a shear moment diagram. Like I said, this is a critical material. Since I occasionally teach solid mechanics, this is, I shouldn't use this word, but this is the source of frustration as a teacher that, hey, oh my goodness, why do those people don't understand and cannot do this simple thing, kind of frustration as a teacher. I think this is one of those. Okay, lots of fundamental concepts we covered in statics will show up in solid mechanics. This is one of the guaranteed items. Okay, so if you don't have a mastery skill this summer right here, right now, I can guarantee you're going to suffer in solid mechanics. And if you suffer in solid mechanics, you're going to suffer in structures 1 and 2. If you suffer those, you suffer in senior design. And you suffer even after you graduate because you don't have a skill. That's the vicious downward spiral cycle. It all starts from this class. So please take it seriously. You know, this is my honest advice for any engineering student because they are bombarded with so many wrong information from peer students. Okay. Engineering could be lots of fun. Major exam could be entertainment if you do the right thing. Okay. All right. Anyways, I'm not preaching, so please stop me, you know, if I start saying those things. Anyways, do you have any question about this shear moment diagram? This is actually challenging because this is composite beam. You have to disassemble, find out support reactions. That's one thing. And also you start drawing the figure. You have to be very careful about sign convention. I think I even made a mistake in my solution and nobody pointed out in the past. I have to fix it today. I'm sorry. You're good, actually. You pointed out. I appreciate it. Go ahead.
So how did you get the area under the curve of the that being the 2.11 feet and the 334 pound-feet?
Yeah. So you want to have a change of moment starting from this point to that point. You know that the moment changes, delta m. That is essentially integrating the function of this thing. That's what the equation says. Basically, the change in the moment is the area under the shear diagram, which is coming from this equation, which is integration of this equation, right? Integration literally means that suppose if we plot the function, you're going to find the area under the curve. That means delta m in the range from here to here is basically how much change of shear do you have. So this area. So this area is equal to this delta m. This delta m from here to here is this area.
And how did you find that area?
2.11 times 316.667 divided by 2 because it's a triangle. Yep. Because you know this is a straight line.
So if you were to do an integral,
yeah,
could you do like integral from 0 to 2.11?
No, not a 0 to. This is like 12 to 14.11, right, in the range of x.
Okay.
With the function given, which is, you have to figure out this function. This is a linear function, which is y equal to ax, y equal to negative ax, and also you have to find out the crossing point. something like that. That's a linear function. So if you integrate that linear function over that range, that is actually, effectively speaking, area under that curve, which is triangle. That's why. Okay. Good point. Any other question? Obviously, shear moment diagram requires practice. So this is your homework assignment. Again, this is, yeah, this is simple beam. You don't have to disassemble. This is actually, by the way, single reaction force, right? So this is simple supported, by the way. So AXAY dy. But you have 8 kilonewton point force and point moment applied here, and then 15 kilonewton per meter things coming up. Okay. So this might take some time. You have to really approach carefully. All right, next one is also homework. Oh, interestingly, this is, again, the beam is supported by 2 wire. Now, wire is quite important. You know, wire only develop tension inside. So you have to basically cut and cut, introduce the tensile force developed inside of the wire, and then tensile internal loading developed in the wire, right? You know it's tensile. And then you know the 45 degrees, that means you know the geometry, that means this is only single unknown, which is the magnitude. And then magnitude is equal and opposite. So 45 degrees means that whatever you found this reaction or support force, you are going to resolve into 2 directions, right? This force and that force, right? This force and that force. You are going to only pick up this force into the diagram. In other words, only shear comes into play. Normal force is equal and opposite. It doesn't come into play for this shear and moment diagram. Okay.
Why do we use the 18-inch?
Good point. I think there's a big secret in it. Let me just take a look at the solution. Yeah. Good point. I appreciate your question. 1/8 of an inch, right? Okay, so this is 310.5. Okay. So what I'm doing here is, because of the 18-inch offset, you know what I'm talking about? Because of the 18-inch offset, you actually create a moment because it's offset. So this is the hooking. This is the point of where you attach the rope. This has an offset of 18-inch measured from the center line of the beam. So it actually creates the moment. It actually creates the moment. So don't forget that moment. That actually affects the internally for shear moment diagram. Oh my goodness, this is sneaky, isn't it? If he didn't answer the question, everybody screwed up this problem, including myself, because I screwed up when I tried to prepare the solution. Very sneaky problem. I don't know who developed it, but cool. So this is shear moment diagram. Okay. So it's almost like somebody saying, I don't care kind of moment diagram. Anyways, so don't forget about this moment developed because of the offset of attachment point. Attachment point here is offset from center line of the beam where you want to draw shear moment diagram, right? Which has an offset of 18-inch, actually creates the internal moment at the attachment point. Okay? You really need to think about it. Okay? Is it good? Is it good? Okay, good. So now you can handle this. Okay. So that's the homework 310.5. Next page. So let's just get into dry friction and wedges. We're going to conclude this 3C today. So let's just think about friction. Friction is quite often it's considered as a resistive force. Okay, so when you try to draw free body diagram, oftentimes you need to consider that the surface, which is touching against another surface that actually has a friction, which develops the resistive force. In other words, if I try to apply the force to move this tripod doesn't move until I apply a certain amount of force. Why is that? Because we have a static friction force developed. Okay, so let's just take a look at it. So friction is defined as a force of resistance acting on a body which prevents or retards slipping of the body relative to the surface with which it is in contact. This is the first case. This is called the static frictional force. Let's just underline here. Static frictional force, Fs. So this is a body with certain weight. Of course, the weight is acting through the center of gravity here. Suppose if you try to push this body with the force P applied. However, you need to have certain amount of force P until this body starts moving, because this body is going to resist your force P by developing static frictional force. Now, static frictional force depends on how heavy this box is, right? In other words, if you put your box, you have equal and opposite reaction force, N is going to show up. That N multiplied by, this is the static friction coefficient, is going to be the static frictional force, Fs. So suppose if you have a huge box and put it on a concrete, very rough surface, you have difficult time dragging it, of course. Okay, so it all depends on two things. One is how much normal reaction force you have. It's usually equal and opposite to the weight of the body. And then how much friction coefficient you have. Okay. Next one is, suppose after you have enough force to start moving this box, you still have resistive force developed. This is called kinetic friction force, Fk. All right. Kinetic because now it's in motion. And then this is slightly lower than static friction force. Typically about 25% lower. So next page, you can take a look at just a plot of relationship between applied force P to the resistive force F developed because of the friction. Now, obviously, for a static force, if the box is not moving, okay, externally applied force P is equal to resistive force P anyways. Yeah, of course, it's not moving. It's an equation of equilibrium, force equal and opposite. But once it starts moving, force Fk, this is kinetic force, kinetic friction force, actually drops about 25%. Okay. So we are going to actually apply equations of equilibrium to find a few different type of problems. Type 1 is, of course, equilibrium. You have a, let's say this is a simple truss structure standing on the ground. Obviously, member AB, member BC. Right here, A is touching on the ground, C is also touching on the ground. You have a different static friction coefficient. Okay. So what is the question? Question is, okay, so how much static friction force is developed at point A and C, stuff like that, that kind of problem. Okay, you can solve that. Second one is impeding motion. You are going to put like a bar, rest against the wall and then floor. Those actually comes with two different kind of friction coefficients. So what is the normal reaction force and what kind of problem can I think? How heavy this bar is if this one stays still. If this bar is this much weight, this is going to start slipping, kind of thing. Okay. So other type of problem is impeding motion at only one point. In other words, suppose if you start applying force P, obviously remember BC is going to be dragged, and then how much resistive force is developed, I guess. That kind of problem. Okay. So let's just take a look at a few examples. Okay. So this is an example problem of typically static only, static friction. Class example 311.1. The uniform pole. The uniform means this pole is made by a single material. Weight of 30 pounds and length of 26 feet. If it is placed against the smooth wall, that means smooth means no friction. And on the rough floor, in the position D equal to 10 foot, will it remain in this position when it is released? The coefficient of static friction is 0.3. 0.3 at A only, I believe. This is smooth. Okay, let me just double check. So this mu s only applies here. This is smooth. Smooth, we assume that the static friction coefficient is about 0. Okay. Now, important thing is, this is a uniform pole. Weight is 30 pounds. What do you mean? Where does the weight acting on this pole?
Probably like the center.
Center of this pole. What is that? Center of gravity. That's right. So if this is uniform, right here bullseye is the center of gravity, right? CG. So how can we determine this CG? That's the subject of next unit, unit 4A and 4B. We are going to find out, okay, what is the CG, center of gravity, center of volume, which is centroid, center of mass, stuff like that. We are going to mathematically determine that kind of location, geometric location, which is next unit. But right now, this is uniform pole, so it's like a bullseye right here in the center, right? So this is where 30 pounds force applied. Okay. So I'm going to draw free body diagram here. So free body diagram, this is the pole, uniform. Okay. And obviously, let's just take care of the geometry first. Geometry-wise, okay. Can we get this height? So you're going to take a look at the triangle. Triangle, this is 26 feet, this is a D, so this is the height, D is 10 foot. Okay, so this is 26, 10, this height is square root of 26 square minus 10 square. So you can get, this is 24 feet. Let's just take care of that geometry. And unknown reaction force, obviously, let's say this is a point B. Okay. So point B, you have normal reaction force, N of B. Okay. Normal means perpendicular to the surface of contact. And of course, right here, right in the center, in the midpoint of 26 feet, you have weight 30 pounds. And then here, once again, normal reaction at location A. This is NA. Okay. And then here, you have to really think about the reaction of the resistive force. This stick, it wants to move to your right, okay? You have to have a resistive force for it. So, of course, you know the direction of friction force here. So this is direction of force, which is the against the direction of motion of the pole, okay? So let's call this is FA. FA is, of course, mu s times NA. Okay. So this is the free body diagram. Then, of course, you're going to now apply three equations, up to three equations available, equations of equilibrium. So I want to probably do as usual. Let's do the summation of the moment. At location A, let's just set equal to 0. This is going to give you, well, this FA and NA doesn't come into play because I'm taking a moment at point A. So you have 30 pounds of weight, create positive moment. What is this? This is half of D, isn't it? So this is 5 foot. Okay. So this is a 30 pounds times 5 foot, creating positive moment around point A. And B create negative moment. So negative normal reaction force NB multiplied by 24 feet set equal to 0. This is going to get you NB. NB is 6.25 pounds. Good. Let's just do some of the force in X direction. Let's just set equal to 0. Right here. And we do know NB is now 6.25. Positive X. 30 pounds, this is Y direction. FA, we don't know, but it's negative direction. Negative FA is equal to 0. Oh, actually, this actually gives you FA. FA is equal to 6.25 pounds. Let's just do summation of the force, Y direction. Let's just set equal to 0. NA minus 30 pounds is equal to 0. This is going to give you NA 30 pounds. Okay. So here's the question. Coefficient of static friction is 0.3. And will this remain in this position when it is released? How do we know? So FA depends on the static friction and also reaction force NA, isn't it? So NA being 30 pounds, you can say max value resistive force of FA is essentially μS times NA. So maximum value is, of course, μS is a static friction coefficient 0.3. NA is 30 pounds. So maximum value is 9 pounds. So required, in this case, 6.25 pounds is way less than 9 pounds. 6.25 is less than 9 pounds. It will remain in the position. Okay. This is easy. Any question? So friction problem, it's kind of easy. So next page is a homework 3.11.1. Determine the largest weight of the wedge that can be placed between the 8-pound cylinder. Oh, this is a cylinder of 8 pounds and the wall without upsetting equilibrium. That means this cylinder starts rolling. The coefficient of static friction at contact A and C is 0.5, but at point B, this is 0.6. So this surface is a very, very rough surface. Okay, so you're going to insert the wedge, but you don't want to start rolling this cylinder. Okay. So the largest weight of the wedge you need. Okay. This is actually quite simple. Okay. Oh, here's another example. Let's just do it. So this is kind of similar to the previous homework assignment. The spool has a mass of 200 kilogram. It actually says mass. Okay, good. So we want to convert it to weight, right? We want to, yeah, okay, let's just convert it to weight. 200 kilogram of mass. So let's just first of all multiply 200 kilogram times 9.81 meter per second square gets you 1962 newtons. Okay, so let's just convert it to weight. Okay. This one rests against the wall and on the floor if the coefficients of static friction at A and B are different. Okay, 0.4 and 0.5. Determine the smallest vertical force P that must be applied to the cable that will cause the spool to turn. So you want to lift up, actually pull this cable to try to spin this spool. So the direction of the spin is this way. So this is something you want to induce the spin. But the contact point A and B produces the friction force to resist it. That's what it is. Okay. So first of all, I want to draw a free body diagram for that situation. So this is the spool. Okay. And this is where the rope is attached to. So you're going to pull this rope. With the force P. Okay. This is the location G where the weight of the spool is acting. And we found this is 1962 newtons. Okay. And obviously right here, the location A, you have, this is a static reaction force, Fa. Fa is obviously mu A times Na. And this is obviously normal reaction force, Na. Now mu A is being 0.4, so let's just simplify. This is 0.4 times Na. That's what the Fa is. And then right here, point B, you have, of course, resistive force, okay, Fb. This is mu B NB. Mu B, the skin friction coefficient, 0.5. This is 0.5 NB. Now, of course, you have normal reaction force, NB. So this looks like the free body diagram. Okay. So let's just apply equations of equilibrium. So I'm going to start with summation of the force in x direction z equal to 0. Let's just put this as a positive x direction. This is going to be Fb minus Na is equal to 0. This actually gives you one equation with two unknowns, which is not good, but let's just write it 0.5 NB is equal to NA. So you got equation 1, two unknowns, NB and NA. Okay. Then you apply summation of the force. In y direction, set equal to 0. Then you have NB plus FA plus P minus 1962 newtons set equal to 0. Let's just simplify a little bit. NB plus 0.4 NA plus P is equal to 1962 newtons. This is equation 2. Okay, and then obviously you introduce three unknowns. Then third equation, you are going to find out sum of the moment. Let's do it at G. If you set sum of the moment at the G set equal to 0, what happens is obviously this FA times this offset distance. Okay. FA times offset distance 0.4 feet. Well, actually meter, right? Meter, 0.4 meter, okay. That's a radius. Plus FB times offset distance, again 0.4 meters, minus P times offset distance, this is 0.1 from G, so 0.1 meter set equal to 0. FA is being 0.4 NA times 0.4 times plus. FB is being 0.5 NB multiplied by 0.4 meters minus 0.1 times P is equal to 0. Simplify one more. This is going to be 1.6 NA plus 2 times NB is equal to 0.1 P. This is equation 3. Again, three unknowns. So now you have equation 1 and 2 and 3 with three unknowns, NA, NB, P. So now you have to do it, okay? Solving equation 1, 2, and 3. Please do it yourself. Please DIY. So if this is an exam problem, of course you have to find out those three unknowns. Can you do it? Let's just practice. So I'll wait for you. So let's just find out three unknowns, three equations simultaneously. What is NA? And what is NB? And what is P? This is your practice to be ready for final exam. Could be next quiz. Only thing I need is this P though. So those two are just, it's good to know kind of information, but I think you probably want to know P.
got like 1881 for B.
1881, yeah. Okay. That's P?
Yeah.
Oh, really?
I got like,
I got 1770.
yeah, I got 36.
Oh, you got that? And then actually for your information, NA should be 245.3 Newton. NB should be 490.5 Newton. Out of that, you should have P about 1370 newtons. It's important to practice because in exam you have to do this anyways. Okay. Any question? Okay, so next page is the last page. This is another homework here. Okay. So this is determine the smallest force P needed to lift the 3,000 pounds vertical rope. That means you need to find out P. Okay. It's kind of similar to what we did today. The coefficient of static friction between A and C, as well as between B and D, are given, which is 0.3, but between B and A is 0.4. Let's just ignore the weight of each wedge. So that means actually kind of make it easier. You don't have to worry about the weight of the wedge. It's just basically how much this 3,000 pounds can be lifted up by applying force P here. Okay. Which is kind of similar to what we looked at this today. Okay. So this is that's it for Unit 3C. Do you have any question about that? This is fairly long, tough unit, 3C. 3B and 3C, those are not easy units, right? Obviously, you should expect maybe a program at least each from 3B, 3C for final exam. It's time consuming, it's not easy. So how can you be successful for that? Of course, bare minimum is, I would say, you did every single homework problem all by yourself and check against the solution. That's minimum. Okay. If you don't do that, don't expect you can do it in exams, obviously. And then I intentionally tried to make the exam problem very similar to those problems. Could be example or homework. Okay. So I guess standard way to be ready for final exam is, of course, you go through your notes, because we spend most of the time going through the notes, doing exercises and take a look at the cross examples to begin with. And then cross example is the starting point of doing your homework. Then, of course, you probably need to spend some time, try to invest your energy and time doing your homework all by yourself. That's important. That's, to me, that's probably the only way to get the real skill set. Okay. Any question about 3B, 3C? Those are the highlights of statics. Highlights of the statics. If you can handle fast program, joint method, section method, and then shear moment diagram, skin friction, lots of system, machines, equation of equilibrium, try to find out support reactions, internal loading. That is the highlight of this class. Those are all foundation of certain mechanics and structures. Okay. You cannot miss any of those. You can't. All right. So having said that, let's move into Unit 4, 4A and 4B. Those are fairly short units. It's going to be done fairly quickly. And then here's the important thing. Those are the, again, suppose if you want to analyze a machine or airplane structure, frame, or anything, obviously, you start with a design. Design need to be done well so that it's strong enough. You have enough factor of safety. It's not going to break down. At the same time, you need to come up with some kind of property of geometry. Property of geometry is quite important. In other words, if somebody gives you this volume, where's the center of gravity of this volume? Suppose if you look at airplane, okay, where's the CG location? That's where you kind of frantically trying to find it. when you design an airplane in your senior year. Location of center of gravity is everything. Your airplane may fly or crash right after you take off. It all depends on the proper set of location of center of gravity, distribution, loading, and then appropriate mounting of engine and everything. You know, it's not a simple stuff, but you need to understand how to get those things. Okay, so we are going to begin with the very conceptual, easy thing. What is the concept? You know, somebody says, okay, so center of gravity. So what the heck is center of gravity, anyways? What is the concept? And it's just to set that concept right. So in this unit 4, 4A and 4B, we are going to talk about center of gravity and then centroid. Those are quite a bit different. Center of mass, center of gravity, centroid, those are all different. Although you use the same equation to find it. Okay, so let's just properly understand. Suppose if you are given a real, like I-beam, how can I find the centroid of this composite shape? There's a method, something called parallel axis theorem. This is the key term. Let me just give you the key term to begin with. Parallel axis theorem. This is a key term you have to master. Okay. So if you're dealing with composite bodies, of course you're going to apply parallel axis theorem. Okay. Composite bodies, even though it looks composite, it is composed of many simple shapes. I-beam is made up by a bunch of rectangular shapes. So each one of those rectangular shapes, you can find out where is the centroid, where is the centroid, where is the centroid. Each one of those centroid, if you know it, you can get the centroid of this whole thing. Okay, that's called parallel axis. Okay, so what is the center of gravity and centroid? The center of gravity, we are going to use the G, or sometimes called CG. That's the location where the resultant weight, okay, maybe the weight of a system acts through. In other words, suppose if you are looking at the 3 particles here. So there's 3 particles in 3D space. Where is the center of gravity of those 3 particles? It's right here, G. How do you find such a thing? Of course, you are going to find out summation of all the weight gives you the resultant weight. And then each one of those particles actually create a moment, right? Because weight is a force going down in negative z direction. So this force creates moment at x, moment at y, not the moment in z though. Moment in x and y is created by each weight of each particle. Okay. So you're going to add up all of those moments. Okay. And then you're going to find out location of x over bar, y over bar, z over bar by moment divided by sum of all the weight, which is essentially defines the coordinate of the center of gravity. Okay, so that's why this equation comes up, summation of all the moment of each axis divided by summation of all the weight of it. Okay, so this is x over bar, x, y over bar, z over bar. This is the location of gravity, center of gravity. Okay. Now, center of gravity is based on the assumption that the gravity of all of those particles are the same. In other words, gravity is constant. So almost always true on Earth. However, if you are seeking astral track, this may not be true. Okay, so the gravity may not be constant throughout the body. Especially designing of spacecraft, you have to really be careful about it. The center of gravity may change because the gravity changes. Okay. But oftentimes we, if that's the case, we're not going to use the word of center of gravity. If the gravity is not a constant, we're going to use instead center of mass. That's right. The center of mass. What opposite? The center of mass is given by assuming that the acceleration due to gravity g for every particle is constant. In other words, W equal to mg. If g is constant, mass is, wait a minute, W equal to mg. Weight is mass times gravity. If the gravity is constant, mass is. So the center of mass is, suppose if it's under the constant gravity, you can actually use the center of mass instead of center of gravity. Sorry about that. I said the wrong thing. Okay, so it looks like the same equation. It's not. Instead of using weight, weight is mg, right? You're going to use m, mass, because g is constant, so you can cancel through out. Okay, numerator, denominator, mg, g is canceled. That's right. Center of mass. This is the center of mass. Okay. How about an arbitrary body? A rigid body of anything is composed of many particles. Particles create the body. Okay. So now instead of summation, you're going to do integral. So you're going to pick up a small, tiny, maybe in this case, volume, dB. This small, tiny volume actually introduces a small, tiny weight to dW. So you're going to integrate over the body. Okay? So you have to be very careful. If you try to integrate this small, tiny weight over the body, what kind of integral do you expect? This is a triple integral. Here we go. So if it's a 3D, if you want to find out center of mass and gravity or centroid, you have to deal with triple integral over the volume. If it's a 3D body, here we go. Okay. Let's just think about a few specific information here. Something called, we are going to introduce specific weight. Specific weight is a weight per unit volume. We are going to use the lowercase Greek character gamma. Specific weight. Okay. Specific weight is a weight per unit volume. By definition, this is how much weight do you have for a given volume of B. B, volume. Okay. So specific weight is actually density times volume. Density times gravity. So. Okay. So specific weight is used instead. dW is gamma dB. Okay. So this actually gives you a density. So density can be used. Suppose if the density is a mass per unit volume. So center of mass can be given by the density. If you know the density. If the density is given for a body, you can determine the center of mass by using the density integrated over the volume. Okay. This is the center of mass. Okay. So there are so many variations of the location of center of mass. Okay. Now for center of mass, assumption is gravity is constant. That's why you can use the density instead of weight. Okay. So here is the actual equations. So next one is centroid. Centroid is again, it's just a geometric center. In other words, if you are given a body of this kind of geometric shape, where is the geometric center of that body? You are not talking about material or density or weight or anything. Just a volume or area or line is given. Where is the geometric center of that given entity? That's called centroid. Okay, so just purely geometric. So if the geometry is given as a function of a mass, you can determine the centroid as a mathematical function. You are going to integrate the mathematical function over a given volume or area or line, determine the location of centroid. This is one of those very primary operation of solid mechanics. So every problem you see, almost every problem you see in solid mechanics, your first question is, okay, where is the centroid? So obviously, if you're dealing with the 3D body, this is a triple integral for each. This is a 2D body, so this is double integral over the area. This is a line integral, so this is a single integral. Okay? So let's say the centroids can be specified by the conditions of symmetry. So suppose if you have the shape has an axis of symmetry, the centroid of the shape will lie along that axis of symmetry. So this is a body which is symmetric about y-axis. So the location of the centroid is along the line of y-axis because it's symmetric about y. Suppose if you have a shape which have a 2 or 3 axes of symmetry, it follows that the centroid lies at the intersection of these axes. So this is I-beam. Where is the centroid of it? This is the crossing point of x and y axis of symmetry, right here. It's bullseye. So this is the 3D body. Where is the centroid? Well, it's essentially, this is the axis of symmetry, x and y and z. Out of those intersections here, this is centroid of this body. It is simple if it's a symmetrical body, obviously. But if you're dealing with non-symmetric body, oh my goodness, all of a sudden it's a nightmare calculation. So coming back and tomorrow, which tomorrow is an online day, okay, we are going to deal with class example 411. Now, I'm actually not going to do any hand math these days. Integral over square root of 4x squared plus 9. Okay, I'm not going to do this. I'm going to actually pick up the software. So I'm going to use MATLAB Symbolic Math Toolbox, okay, tomorrow's lecture. Okay, so if you're willing to use the MATLAB, please install your MATLAB and be ready for tomorrow's online lecture. Okay, I assume you have laptop or desktop, right? And then you have free access to MATLAB. MATLAB is free for you. Did you know that? Did you? If you have no clue, please give me a text Microsoft Teams today. I'm going to walk you through it. Okay, you're going to install your MATLAB on your laptop or desktop, either way. Then be ready to go with me. You know, we're going to use Symbolic Math Toolbox to do all the math in this unit. I'm not going to do hand math, so be ready for it. Okay. Let's stop here today. Any question? All right, have a good day. We're going to see you tomorrow online. Be ready with MATLAB.